point theta 2 here. Okay, and because this function is contains two variables here, and sometimes it's very hard to visualize this function in high dimensional space. So in many cases, people visualize them in terms of these contour lines. So in this contour lines here, what's drawn in this case here, it essentially represent this. Along this circle here, for all the points within the circle I have here, the loss function have the same value, has this exactly same constant values there. So let's take examples here. Suppose loss function along this contour here is 100. Let's take one example of that. Suppose this is equal to 100 here, and then this contour line is 90, this is the 80, this is the 70, this is 60, and then there's this minimum point here, okay? And you can see when I go circle from the outer circle to the inner circles here, the loss function becomes smaller and smaller and smaller. And I represent the functional formula through this type of contour lines of that. So then for visualization purpose of that. So you can see in this representation here, the minimum point of this loss function will be this point here. Exactly, look at the center of those contour lines of that. And the question is, how do I identify these optimal solutions of these guys here? And then if I know this point here, essentially the optimal point, first index here will be theta 1 star here, and this will be corresponding to the theta 2 star here. And entire optimization process is trying to identify this point. And the question, how do I solve the problem of that? So iterative method is saying this, well, what I do, I start with a randomly initialized theta here. Suppose I randomly initialize the theta here. So this is my first theta here. This is my theta. I can put the index here, theta 1 here. This is initial randomization. So random initialization of theta here. And next what I can do here, I'm going to update the theta here through a small step. And in order to update them, I need to calculate the directions. Where should I go? I'm going to go this way or go downwards, right? Remember now I represent the parameter in a two-dimensional space. So theta can go either way, right? So suppose I can say theta can go this way. If I want to draw randomly here, I can update the theta this way, and then next this way, next this way, next this way. So that would be one path I can go, right? But this path is not good, right? So that doesn't go toward my center of that. The center is my optimal solution. Ideally, I want to do that. And so that's what you can see, try to identify the direction is kind of important for implementation of the algorithm. And what the gradient descent methodology is saying is, well, in order to know the direction I should move my theta here, what I do, I first calculate the gradient of these loss function at exactly at this point here. So what is the gradient here? Okay, and what it's saying, well, gradient here will be, in general, will be orthogonal to these lines here, orthogonal to this contour line. So that's by more or less by the definitions of the gradient, the place where the loss function changes the most. So changes the most. That's in local sense, right? So that's the gradient here. If you're along this direction here. And along this direction, let me remove this here. So along these directions, my loss function increases most, and the increases the quickest way, right? However, this is point to increasing direction. If I want to point to the decreasing direction, the minimal of this loss function, I'm going to reverse that. So that's the reason I'm going to point to the opposite direction. But instead of pointing this way, my delta theta will be pointing this way here, pointing this way. So this is my delta theta. And then I'm going to need to choose step size, say, how far should I go? Should I go to this? Because direction will be always this, any point will be along this direction. Should I go here, or here, or here? And if I say, if we go in this side here, maybe that's not optimal because the loss function at this point here is higher than the point, this point of that. So ideally, so maybe I should point this direction now. So you have to choose a step size. So how far you should go? Well, so that is determined by this alpha parameter, step size. Well, so what I'm going to do here, I usually choose alpha to be small, so I'm going to point this way and move my theta from this point here to this guy's here. And then you say, this is my initial theta here. This is your initial, your first random initial theta. So now you have the new updated theta here, called theta 2. Let's do it this way. And that now, once you are in the theta 2 positions, and then what you need to do here is this, you need to update the direction again, because you need to calculate what is the gradient at this new point here, new theta 2 here. And then what you say, I'm going to update it toward the gradient direction here. That will be this direction here. And then you say, choosing a step size, you get theta 3. So that will be updated parameter theta. And after you get the theta 3 here, you determine direction delta theta. So that will be the gradient. You calculate the gradient again. The gradient will be orthogonal to the contour lines here. It will be this way here. So that, and then you get theta 4. And then at theta 4, you calculate the gradient again. You can see point this direction there, and so on. So in the end, your point here will getting closer, closer, closer. In the end, maybe after 10 iterations here, you are getting closer to your optimal solution of that. So this entire path here is this iterative method will give you, go along this way, this way, this way, and this way. In the end, you reach your optimal solutions of that. So as you can see, you implement this algorithm here, you need to determine what's the direction. And then based on gradient descent methodology, that is based on the opposite of gradient of that. And secondly, you need to determine the step size of this function. So that's called a gradient descent methodology.